Okay, you guys, so I was asked to do a video on the squeeze theorem, and I'm glad because I've forgotten all about it. There's just so many things I'm trying to remember to do and looking through the list, and I thought I did everything. But anyway, the squeeze theorem is pretty straightforward, and I'm using this Wikipedia picture here to show you what it means essentially, but this is the squeeze theorem in a nutshell. So this is not the formal definition, but it's formal enough, okay? Squeeze theorem says you have three functions, f, g, and h. And they're positioned such that h is in between f and g. And the limit as x approaches a particular point of f equals some number, and if the limit as x approaches that same point of g equals the same number, then it makes sense that if there's a function in between those two, it would also have to approach that number. So as a visual, I'm going to make this a little smaller, pop it up there. I found this graph, and we'll call this green function f, we'll call this red function g, and then of course there's a function h in between, right? And if we look at the point, say x is equal to 0, well, the limit of f as x approaches 0, right, from the left and the right, in order for the limit to exist, is 0. And if we look at the limit for g, well, as we approach from the left and the right, the limit of g is, as x approaches 0, is 0. So what the squeeze theorem states is that if we have this function h that's in between f and g, at this point x equals to 0, h of x must also have a limit of 0. All right? Okay, so let's do a couple of problems so you can see. So the first one, first example, f of x is equal to negative 1/3 x cubed plus x squared minus 7/3, and g is equal to the cosine of pi x over 2. Now you may be wondering, well, why isn't there an h? A lot of times you're not going to get an h, and most of the time they're going to give you one function and you're going to have to come up with two out of that. You'll see what I mean in a minute. So let's just take the limit of what we've got. This is all I have. They want us to find the limit as x approaches 2. So I say the limit as x approaches 2 of f of x is equal to, this is nice because I can just plug the 2 in, right? It's polynomial. So 2 cubed is 8, and 8 times negative 1/3 is negative 8/3. 2 squared is 4 minus 7/3. And negative 8 and negative 7/3 makes negative 15/3, and negative 15/3 is negative 5, right? And so we get that that limit is negative 1. Now we're going to do the same thing for g. So if I plug the 2 in, so you notice how I'm writing this, right? I'm showing the grader. I'm going to take the limit as x approaches 2 of this function, and now I'm going to plug that 2 in, right? So that means the limit notation goes away. So this is 2 pi over 2, and those are going to cancel. So what we're looking at is the cosine of pi, and that limit is negative 1. So I can say that since the limit as x approaches 2 of f of x is equal to negative 1, and that's the same as the limit as x approaches 2 of g of x, then that's going to imply that the limit as x approaches 2 of h of x is also going to be negative 1, even though there's no third function that I'm calling h there. Okay? All right, now let's look at something a little weirder, but it's not hard. So a famous example is the sine of x over x. And I had a couple examples here. What did I do with them? I think I threw them away. Yeah, I think I threw them away. Well, let's look at sine of x over x. So let me move this thing. I'm also doing, I have a million tabs open so I can use pictures for pre-calc too. So, all right, so we're going to have f of x equals to the sine of x over x, right? And I want you to find the limit as x approaches infinity of this thing. Well, first of all, you're like, I don't have a g, I don't have an h. It's okay, you're going to find them. When you have a trigonometric function, the first thing you want to do is write down what you know about the sign. You know that the sign lies in between positive and negative 1, right? So you want to write this little inequality, okay? And that's probably a point right there, because you're showing the grader mathematically that you understand that the sign falls between positive and negative 1. And so does the cosine. But the problem is this function is sine of x over x. And the goal is to get this thing in the middle to look exactly like the function that was given. We want those two to look alike. So how do we do that? Well, we can divide each piece by x. So we'll have negative 1 over x is less than or equal to sine of x over x less than or equal to 1. And now that that middle piece looks exactly like the original, now I can, oops, forgot the x. Now I can take the limit of each one of these functions. So see, before here, I had this function sine of x, but I didn't have another one. Now I have two, and this function is sandwiched in between those two functions. Make sense? So we have the limit as x approaches infinity of negative 1 over x. Well, if I plug infinity in, I'm going to get 1 over infinity, which is 0. And then I show the limit as x approaches infinity of positive 1 over x, and again I'm going to get a 0. And since both of those limits equal to 0, I can say, therefore, the limit as x approaches infinity of the sine of x over x equals 0 by the squeeze theorem. You want to state the theorem. Okay? It's also called the sandwich theorem or the pinching theorem, and I think it's really called the squeeze theorem, so I would stick with that lingo. I wouldn't deviate, but I think they accept both of them. Let's see, I also pulled up, is this the one? Yeah, some other ones. So I'll do a couple more examples. So let's look at this one here. Alright, so I'm just gonna work over here because I'm wasting so much paper doing this. Alright, so it's asking you to compute the limit as x approaches infinity of 2 minus cos x over x plus 3. And can we please focus? There we go. Okay, so I have that trig function in there. So again, I'm going to do this because this is true. Now, you have to be careful here because there's a negative sign right here, and this is not negative. So to alleviate that, I'm going to multiply every term or every piece by negative 1. When I do that, two things are going to happen. Not only is it going to change the sign of all the pieces, but I can't forget to flip my inequality symbol, because remember, when you're dealing with inequalities, whenever you multiply or divide by a negative, you have to flip the inequality symbol. So if I multiply this by negative 1, I get a positive 1, greater than or equal to negative cosine of x, greater than or equal to negative 1. And then I'm just going to write this from smallest to largest. So I'm going to write negative 1 is less than or equal to negative cosine of x, which is less than or equal to 1. So I'm just flipping this thing around so that way it's in ascending order, so to speak. Okay, so again, I got to get that middle piece to look like the original function. So I guess what I can do now is I can add 2 to every piece, right? So if I add 2 to negative 1, I'm going to get a positive 1, less than or equal to 2 minus cos of x, less than or equal to 3. And now all I have to do is divide every piece by x plus 3. And they look the same. And this thing is sandwiched, or I can't say squoze, that's not a word, is it? So it's in between two other functions. So I'm going to take the limit as x approaches infinity of 1 over x plus 3. If I plug infinity in, I get 0. I'm going to take the limit as x approaches infinity of 3 over x plus 3. And again, you see I'm writing each one because the grader is going to want to see that. And that's also 0. So since the limit of the function on the left is equal to the limit of the function on the right, then I can say, therefore, the limit as x approaches infinity of 2 minus cos x over x plus 3 is equal to 0 by the squeeze theorem. Right, and yeah, this thing has some solutions here, so let's just look at it just so you can see. Oh my. Okay, so there it is. Okay, you see each limit. And by the way, this is a nice, this way, oops, didn't mean to do that. This right here, right, like what is in the formula or the sort of informal definition, it's really nice and easy to, if the limits are equal for both functions, just say, the limit of one function equals 0 equals the limit of the other function, and you're good. All right, let's do one more from here, and then you can come here. You can see this is math at ucdavis.edu. I think it's called visual calculus. I'm not sure, but anyway, it's math.ucdavis.edu, and I suppose if you go in there and just type squeeze principle, I just Googled squeeze theorem examples, and this is one of the ones that came up that seemed to have a couple of pretty good problems. Okay, let's look at this one. Oops, sorry. Too many videos, so little time. All right, I'm probably not going to be able to fit any more in this one, so let me just put those in the trash can. All right, so let's have a look at this one here because it's kind of cool. We've got, oops, where am I here? Here we go. We want to find the limit as x approaches 0 from the left of x cubed cosine 2 over x. Now you notice this isn't cosine x anymore. It's got 2 over x in it, but that's okay. It's still got that trig function. So I'm going to say -1 is less than or equal to cosine of 2 over x is less than or equal to +1. Okay. And now there is an x cubed. I got to get the middle piece to look like the original. So all I'm going to do is multiply every term both sides, or every piece by x cubed. So when I do that, I'm going to have negative x cubed is less than or equal to x cubed cosine 2 over x less than or equal to x cubed. Now, here's the thing. I didn't flip the inequality, but you need to. Why? Because this limit here, so this is a tricky one. This limit here is x approaching 0 from the left. Okay? So that means we're taking negative values of x. It's approaching 0 from the left. Remember, if I plug a 0 in here, I have division by 0, I've got an issue. So if I'm coming in from the left, the values have to be negative. So be really careful with that. So I made this an additional step. But what we're going to do is, essentially, we're going to change this to x cubed greater than or equal to x cubed cosine 2 over x. Now I'm not multiplying by negative x cubed, but the values of x are negatively valued. Does that make sense? Greater than or equal to, this will become negative x cubed. The values of x are going to be negative, and when you cube a negative, you get a negative. All right, so here it became positive because I had a negative x cubed. So if I do like a negative negative 2 cubed, I'm going to have a negative 8 or a positive 8. All right, so here it was already negative, so that's going to become positive. But because the values are negatively valued, if I'm multiplying, I have to flip the inequalities. Now I'm going to rewrite this like so. Right? My middle piece matches what was given. So now I'm going to take the limit. The limit as x approaches 0 from the left of negative x cubed, well, that's 0, right? And the limit as x approaches 0 from the left of positive x cubed is also going to be 0. Right? We're getting really, really, really close to 0. And so what I can say is, therefore, the limit as x approaches 0 of x cubed cosine 2 over x is also equal to 0 by the squeeze theorem. All right, and that's it. And I would suggest you come here and, do a little bit more practice on some of these. Ooh, look at that one. That's going to be a good one. So yeah, it looks like they got some pretty good problems in here. This is also very famous. You probably find that one in your textbook. I don't know if they're going to go to the extent of giving you something like this on a 25 or 20-minute test, because that's going to take too long, but hey, you never know. So anyway, give those a whirl. I'll try and find some squeeze principle problems in the AP classroom between now and Friday anyway, so you can get a little bit of practice AP style in. And anyway, let me know if you have any questions. Have a good night.